So, a really interesting twist I would like to kind of help you appreciate today. So, for coherent states, we do know that there is a certain uncertainty in the electric field and a certain uncertainty in the number of take it. We observe that for a coherent state, our electric field E1 varies with time like an oscillator. Okay, so we tried this relationship in our previous lecture. Today I'm going to show you that this is not just a pure nice curve without any uncertainty, rather there is some uncertainty associated with this curve. There's some width to it.
ये ना इसकी वजह से बैटरी बदलना है अभी किया अभी कुछ सही आवाज नहीं आ रही है
फर्क नहीं पड़ता बड़ा तो मसला हो गया Alright, so how do we approach this problem? The first thing that we would like to do is that for a coherent state, we would like to find out the expectation value of Ex, right? That's the first thing we would like to do. And this should look like a harmonic oscillator. Okay, we do know that Ex dt, this is given by E omega sin kz, and the position operator, which is the sum of these latter operators. This is something we already know about, and we've looked at this from previous relationships. So if I were to take the expectation value of Ex, this would become E omega sin kz alpha A plus A dagger alpha. Correct? And this, of course, becomes E omega sin kz alpha plus alpha star. Which of course is 2 times E omega sin kz and real part of alpha. Correct? Actually, we need a time dependent term here, alpha t. So because this electric field is time dependent, so what we could do is we could replace these alpha, these A and A dagger by the time dependent counterparts. So the time dependent, so if you really want to impart time dependence here, as I showed in the previous lecture, there is an EI minus omega t here and an E plus I omega t here. This is something you could derive from the Heisenberg relationship. Okay, so this relationship gives you the time-dependent forms of these letter operators. जी ये भी कर सकते, उससे भी कर सकते। So this is really alpha, the real part of alpha t, which is alpha E minus I omega t. Correct? So suppose alpha is a real number. So this is our final result. This is our final result. If alpha is a real number, let me suppose that alpha is a real number, so this becomes 2e omega sine kz cosine of omega t. Correct? If alpha is a real number. So my expected value of the electric field goes like a sinusoid because of this cosine omega theta. So a coherent state resembles an oscillator. It just changes with time in a sinusoidal fashion. But there is some finite width of this oscillation. There's some uncertainty associated with it as well. In order to find the uncertainty, what we really need to do is we need to find Ex square as well. You need to find this object. Because then from this object we can determine what delta Ex is. So if we were to determine Ex square, so we just start from here. This will be E omega square sine square kz, and then I put bra alpha. I need the square of this. So if I take the square of this, I will get alpha square E minus 2i omega t plus alpha star squared E 2i omega t plus alpha into alpha star is alpha mod square times 2. Correct? इसको करना है. Sorry. Plus a dagger, time independent because the ei omega t's cancel out, plus a dagger a acting on the coherent state. This is what we have.
Displacement, the expectation value of electric field element is zero नहीं होगी क्योंकि जब वो रेज और लोड करते हैं स्टेट को तो
नहीं, क्योंकि when a acts on alpha it gives me alpha, and in the reverse alpha dagger acts on alpha to give me alpha star. This is an eigenstate of a. This is not a number state. Alright, so we proceed from here. The action of this term and the action of this term on alpha needs to be calculated. Right? So when you do all, and this thing can be replaced, I think, by 1 plus 2a dagger a. Okay. So when you do all of this, the final result looks like the following. E omega square sine square kz 4 alpha square cosine square omega t plus theta I don't have a theta, right? I can insert a theta here if I want to. I don't need to have this real, in fact, I can put this alpha to be equal to alpha ei theta, right? So I can really have alpha theta minus omega t, correct? So cosine square of theta minus omega t plus 1. This is my ex square expectation value. ये जरा 2-3 मिनट लगाओ, जरा करो प्लीज, इसको जरा करके देखें. Remember, a square of alpha is alpha square alpha. Remember this. Where alpha square is not the modular square, it's pure alpha square. If I take the conjugate of this, bra alpha, alpha diagonal square is alpha star square bra alpha. Okay, so keep these relationships in mind. So try to derive this, please.
क्या करना है सर?
इसको ड्राइव करो ex square को. Which is ex squared minus ex squared under root. This turns out to be e omega sine kz. Right, so this is the uncertainty in the electric field. So this will be the width of this curve. So the expectation value of the electric field is given by a nice sinusoidal function, like any oscillator, but there is a finite width to this. There is a finite uncertainty associated with it. Chalk, it's a bad chalk, that chalk. So there is this uncertainty associated with this coherent state. Now, the beautiful result is that for a coherent state, if I look at the uncertainty of the coherent state, this is what it is. And if I look at the uncertainty of the vacuum state, it's exactly the same. So this is also equal to the uncertainty in the vacuum state. For the vacuum state, we know that the average electric field is 0. And there is only fluctuation, there is only ex square expectation value is non-zero. And that equals delta Ex for the vacuum state. So the coherent state and the vacuum state have exactly the same uncertainty. Now if I were to plot the vacuum state on my phase space, it looks like a very nice symmetrical blob here, a circle at the origin. And it has minimum uncertainty. This width is 1/2, this width is 1/2. And the product of the uncertainties in the two field quadratures is 1/4. And that's at the minimum. The coherent state has exactly the same uncertainty. So the size of this blob in the phase space for the coherent state is exactly the same. It's only that it is displaced by alpha modulus. Okay? So this is my coherent state. Minimum uncertainty, no doubt. Some phase uncertainty given by this opening angle. The distance from the origin of the phase space depends upon the alpha, the magnitude of alpha, right? And so first of all, so if you have a larger electric field, alpha will be larger, correct? So when alpha is large, the blob size doesn't change, right? The blob size doesn't change, only that the coherent state goes further away from the origin. Alpha goes up. Its magnitude goes up, and we've already seen that the alpha corresponds to the magnitude of the electric field. And this opening angle, by the way, decreases. So the phase uncertainty goes down as the magnitude of the electric field goes up. But the great point is that the coherent state and the vacuum state, they are just related by displacement. Okay? So in fact, we can define the coherent state as a displaced vacuum state. And there's another operator that is very useful in quantum mechanics and quantum optics. That's called the displacement operator. Whatever displacement operator is equals to. So let's define a displacement operator. I define a displacement operator through a distance alpha in the following fashion. E raised to power alpha A dagger minus alpha star A. This is my definition for a displacement operator. Alpha is some complex number. Let's see what happens when this operator acts on vacuum. So if I take my displacement operator and have it act on vacuum, let's see what happens. So this becomes E alpha A dagger minus alpha star A acting on vacuum. But the point is that A dagger and A don't commute with one another, so I can't break this up. So, but I have a theorem which is called the Baker-Campbell-Hausdorff formula, that if I have E, A plus B, then this becomes EA, EB, E minus AB over 2 if there are two things. If the commutator of A and B is not 0, if the commutator of A and B is 0, then this will be true. But the commutator of A with the commutator of AB equals the commutator of B and the commutator of AB. And this is 0. So if this is true, then this formula holds. That's a very useful formula, by the way. It's frequently ubiquitously used in quantum optics. So now let's suppose this is my A and this is my B. I do know that A dagger doesn't commute with A, but I do know what the commutator of A dagger and A is. It's minus 1. It's a scalar. So I get a scalar here. A commutes with any scalar, B commutes with any scalar. So this holds true if I take this to be A, capital A, and I take this to be capital B. Right? So I can split this up. I can split this exponent into smaller exponents. I do, however, need to compute the commutator of this object with this object, right? So let's proceed with this. So first of all, I assume that my capital A is alpha A dagger, and my B is minus alpha star A. So let's compute the commutator L A B. This is minus alpha mod square A dagger with A. This is plus alpha mod square, right? So my displacement operator acting on vacuum becomes E alpha A dagger E minus alpha star A and some scalar. Let me put down the scalar over here. E minus alpha star over 2, and this acts on vacuum. Now, let me expand this exponent. Since I do know that the lowering operator acting on 0 once is going to give me 0. So this is really, this looks like this. E minus alpha square over 2 E alpha A dagger. This really is minus alpha star A sum raised to power P over P factorial, sum over all P's from 0 to infinity, and this acts on ket 0. Now only when P equals 0 will this give me a non-zero number. Right? So this, all of this becomes E minus alpha square over 2 E alpha A dagger. Right? And so when P equals 0, this is 1 over 1 acting on, this is ket 0. Alright? Yes. So G alpha is E minus alpha square over 2. Let's break this up. Alpha A dagger raised to power n ket 0 n factorial, n goes to 0 to infinity.
Coherent state,
Right, so this is actually the coherent state, and you can prove that. So this is E minus alpha square over 2 alpha raised to power n
and
A dagger raised to power n acting on 0 n factorial. Isn't this the coherent state?
yes,
This is the coherent state, alpha. So the action of the displacement operator through alpha is that it converts this vacuum state into a coherent state. Yes?
So what different size the vacuum state alpha and displacement operator is alpha?
Beautiful. See.
सर जो कोहेरेंट स्टेट होता है उसमें n फैक्टोरियल का स्क्वायर रूट नहीं होता
N factorial का square. होता है. So A dagger n. क्या गलती क्या हो रही है फिर? Over n, 1 over n factorial alpha raised to power n, Now this is n factorial square root get n. Right? Because a dagger, since a dagger acting on 0 gives me 1, a dagger acting on 1 is under root 2 get 2, right? So this is under root, this is a dagger square, a dagger 1 acting on 0, right? Is whether so there's an under root n here, and this finally becomes e minus alpha square over 2 n, alpha is for n, and factorial square root get n. Alright, so this is the coherent state. So the displacement operator creates a vacuum state into a coherent state. And the second question in the homework will be about the displacement operator. First of all, the displacement operator is used. Right, so this is something I will ask you to prove. The displacement operator is such that if I take the dagger of the displacement operator, that is the inverse of the displacement operator, which is really the displacement operator acting through minus alpha. Okay, so I can bring a coherent state back into vacuum. The other nice thing about the displacement operator is that if I have the displacement operator acting on vacuum, it creates a coherent state. If I follow this up with another displacement operator, I will move one step further, so I'll go to alpha plus beta up to some global phase. So the displacement operators form a subgroup. Okay, and displacement operators are really important. So displacement operators together with this Baker-Campbell-Hoster formula is a very important technique that is employed in quantum optics. So now we have two definitions for the coherent state. One definition is what I've written over here. It's a superposition of number states weighted by a certain coefficients. And if we also know that for coherent states, if you were to find out the probability distribution of the number of photons is Poissonian. Keep that in mind. For number states, it's a Dirac delta function. So coherent states give you Poissonian statistics when they are detected. And the second definition for the coherent state is that the coherent state really is formed by the action of the displacement operator on the vacuum state. Now, what I would like to kind of show now is like to do a calculation on how these coherent states evolve with time. But before that, I would like to describe how these coherent states look like in the position representation. How do they look like? So I cannot write down the wave function for a number state. It's impossible to do that. Okay, I cannot write a wave function for the photon, but I can write the wave function for a coherent state. Okay, so let me try to do that. So now my task is, I want a positional wave function for the coherent state. See what it looks like. Okay, you do know that if you have a harmonic oscillator, then its eigenstates in position representation, they are called harmonic polynomials. So we know what the wave functions look like when we solve a harmonic oscillator problem, right? And the solutions for the harmonic oscillator are the number states. But the coherent state is not a number state, it's a superposition of number states. So we would like to see what does the coherent state really look like. So now if we want to approach this problem, so how do we do that? So I've done some calculation to help you in that respect. So what I really need is I have my coherent state alpha and I want to write this in the position representation. Okay, and I do know, so basically I would like to write Q D alpha get 0. Q E alpha A dagger minus alpha star A acting on get 0. This is what I'm interested in. Now I can use the same formula that I already have. And I just would like to do that now. This, of course, is going to give me e raised to power minus alpha square over 2 bra q e alpha a dagger acting on get 0. Correct? Now what I would like to do, I would like to express this raising operator in terms of position and momentum operators, so that I can take this bra and move it through and get a wave function here, which will be the ground state wave function for the vacuum state. And I already know what that ground state wave function is. It's a Gaussian. It's the lowest order Hermite polynomial. It's a Gaussian. Okay? So I would like to convert this A dagger into position and momentum operators, and I already have the formulas for that. I do know that my from my earlier ramblings that my A dagger is x1 minus iota x2, right? This is proportional to a position operator and this is proportional to a momentum operator. Okay? And I do know that this is x1 is omega over 2h bar 1/2 q minus I x2 is I 1 over 2h bar omega 1/2 p. Right? I do know this. Got it? So this is my A dagger operator here. I can express this in terms of a position and a momentum operator. I just do the inverse transform. Initially I had expressed Q in terms of x1. Q is proportional to x1 and this P is proportional to x2, right? Alright, so far so good. So now I kind of try to substitute h bar over omega. This has dimensions, this object has dimensions of position, q naught. I call this q naught. So the advantage of this is that this becomes 1 over 2 q over q naught. This object becomes this minus iota over under root 2, and then I need h bar over omega, h bar over omega, okay, q naught over h bar I put in h bar here. That h bar over omega under root becomes a q naught, and I need to multiply with an h bar in the denominator, this called h bar square root h bar in the denominator p. So this is my A diagram. Okay, now I insert this A diagram in here. So please follow this carefully. Probably couldn't find this derivation anywhere in a kind of closed fashion. It's hard to find. So this wave function in the position representation looks like this: E minus alpha square over 2 Q E alpha over under root 2 Q over Q naught minus I alpha Q naught over under root 2 H bar P, and this acts on get 0. Now I can, so this is a differential operator, this is just a position operator, so I can move this bra around and I can put in the wave function for this state. The wave function, which is the ground state of the harmonic oscillator, that wave function just really looks like a Gaussian with some form C naught E minus omega Q squared over 2H bar. Alright, which is C naught E minus Q squared over Q naught squared is 1/2. Okay, so C naught is some normalization constant. You can also find that normalization constant. This we found in one of our classes. This was the ground state wave function for the harmonic oscillator, for the vacuum state. Right, and it's standard in any textbook which describes harmonic oscillators. So what I could now do is, in order to find out the ground state wave function, Q alpha E minus alpha square over 2. Now I have E alpha over under root 2 Q over Q naught E minus I alpha Q naught over under root 2 P over H bar, and this acts on some C naught E minus half Q square over Q naught squared. Now what is this object here? This is a standard object in quantum mechanics. What is this? It's a momentum operator with a minus iota some magnitude and momentum over H bar. What does the momentum operator do when it's exponentiated? It becomes a generator of translations. So it's a translational operator. It generates translations. If I had angular momentum here, it would cause rotations. So remember that if I have E raised to power minus I some magnitude x naught px over h bar, and this acts on a wave function, then the action of this generator of translation is to shift this wave function by this amount. Okay, so this is something you learn in your first course in quantum mechanics. The momentum operator translates a wave function in space. Okay? This is a Hamiltonian translates in time. Momentum operator translates in space. Px translates in x, py translates in y, pz translates in z, and you will prove this.
So जो x operator है वो p space में translate करेगा भी.
जी बिल्कुल. X operator translates in the momentum space. बिल्कुल. They are Fourier counterparts of one another. So now with this relationship, I could immediately write this object as now q has to be displaced by this much. Correct? So my wave function becomes C naught E minus alpha square over 2 alpha over under root 2 q operator divided by q naught E minus half q naught squared. This q is now to be translated. This is a position variable. It has to be translated by alpha q naught over under root 2 and square, of course. Okay? So now when this happens, this is also a Gaussian wave function. It's just that its center position is changed. Right? And if I were to make this time dependent, you'll see that the centroid of this Gaussian wave function is varying. It's going as a sinusoid width. So you already have a hint of what this wave function looks like. The wave function looks like a Gaussian. And if I were to, now this is a position operator that is exponentiated, that is acting solely on position variables. So I can replace this operator just with the number itself. So this becomes C naught E minus alpha square over 2 plus alpha over under root 2 q over q naught minus 1 over 2 q naught squared q minus alpha q naught over under root 2 whole square. So all of this is the power of the exponent. This is my wave function for the coherent state in the position representation. Now I can improve this further by completing the squares, etc. But please.
अच्छा जब आपने वहाँ पे Q और P के E's को ब्रेक डाउन किया तो फिर वो एक एक्स्ट्रा
Oh sorry, कोई एक्स्ट्रा टर्म आनी चाहिए. मैं भूल गया. Sorry, शाबाश, good point. I forgot to add this. So when I break this up, I need to add another factor, which is, let's find the commutator of this factor with this factor, right? Sorry, मैं भूल गया. Thank you, Dr. Nanika. So if I take the commutator of alpha over under root 2 q over q naught, commutator with minus I alpha q naught over under root 2 p h bar. Right? I need to find this commutator. And then give it a minus sign divided by 2. That factor is also going to come out. So this gives me minus iota alpha square. Remember, it's not alpha mod square, it's alpha square. Q naught 2 Q naught h bar, and the commutator of Q and P, which is iota h bar. So this h bar goes away, q naught goes away, and I'm left with minus iota square is alpha square over 2. Right? So there is really another e raised to power minus alpha square over 2. Not an alpha mod square, an alpha square over 2. So I want to put that term here, e minus alpha square over 2. वो माइनस फॉर्मूले से आ रहा है, ये वाला माइनस, right? So there's a minus sign here. Actually minus alpha square by 4 आता है, sorry. 4 आता है. So this is our position wave function. it's a displaced Gaussian. Now what I could do, this factor is independent of Q, this factor is independent of Q. These two factors have Q in them, so I can do a completion by the squares kind of approach. Okay, so let me give you the final result for this. Let me calculation. कैसे करें इसको? थोड़ी सी कोशिश करके देखो. So basically, what we need to do is, I'm just going to write down the power here. So I have minus alpha mod square over 2 minus alpha square over 4 plus alpha q over under root 2 q naught minus 1 over 2 q naught square q square plus alpha square q naught square over 2 minus under root 2 alpha q q naught. Right? So this is the power here. So I'm just giving you a hint of how to proceed with this. So this is minus alpha mod square over 2 minus alpha square over 4. So this term is independent of Q. So I can put in a minus 4 alpha square minus alpha square over 4 here, right? So this becomes half. So I'm left with plus alpha q over under root 2 q naught minus q square over 2 q naught square. Let's keep this outside. Square q square, वो टर्म बाहर चली गई, minus 2 alpha q q naught. Correct? Got it? So this becomes what I would like to do now is minus alpha mod square over 2 minus alpha square over 2 minus 1 over 2 q naught square q square minus under root 2 alpha q q naught. Alright, and then I want to put this inside the bracket, so I put minus 2 q naught square alpha q under root 2 q naught. Correct? So this is a to the plus. So this term I just bring inside the brackets. Okay, so this means that this 1 the q naught goes away. Okay, so this becomes alpha q q naught square root 2. So this becomes minus 2 under root 2 alpha q q naught. Right. So now I want to complete the squares. This becomes minus alpha mod square over 2 minus alpha square over 2 minus 1 over 2 q naught square. This is q squared minus 2 q under root 2 alpha q naught plus 2 2 alpha square q naught square minus 2 alpha square q naught square. Right? This becomes minus alpha mod square over 2 minus alpha square over 2 minus 1 over 2 q naught square. This becomes q minus under root 2 alpha q naught squared plus alpha square are 2 q's plus alpha square minus alpha square, this becomes plus alpha square. Right? So this is my final result. So what I could do now is, there's another thing that I need to do really. And that thing is, if alpha is real, everything is simple, so there's a real number here. Right? So this is real, everything is real. But alpha can be complex. So if alpha is complex, this alpha square becomes alpha real square minus alpha imaginary square plus 2 iota alpha real, right? So things get a bit more complicated. And this becomes alpha real plus imaginary square as well. So overall, what the next step that I would like you to do on your own is the following. So take alpha to be some real number plus iota times an imaginary number. If I were to do that, I just insert this expression in here, I will get terms which will have iota with them, and those will act as global phases. All the iota terms will act as global phases, and I can ignore them. At the end, I will just have a real number here, alpha prime. So if you open up this bracket again, you just get a real number. All in all, the final result looks like the following. Eventually, your wave function hello. Your wave function will have a C naught some terms with some function of alpha and alpha double prime, right? You're just taking the terms without an iota. And e raised power minus 1 over 2 q naught squared q minus under root 2 alpha prime q naught squared. Yes, please. Yes, some function of alpha and alpha. So compute this. So this is a Gaussian whose centroid has been displaced by some amount, alpha prime q naught. Alright. So this is a positional representation of a coherent state. It's a Gaussian. It's a Gaussian pulse. It's also called a wave packet. Now, if I would like to see how this state evolves in time, what would I do? I need to look at the time evolution. So in order to look at the time evolution, suppose I have some state alpha at time t equals 0. And this, on this state acts the time evolution operator is minus iota h bar t over h bar, Hamiltonian t over h bar. So this becomes e minus I t over h bar. Now what is the Hamiltonian? The Hamiltonian is h bar omega, the number operator, a dagger a, plus 1/2. Correct? And this acts on my number, on my coherent state, minus alpha square over 2 alpha raised to power n, right? Get n over n. This is my coherent state. Got it? So all in all, this becomes n e minus alpha square over 2 alpha raised to power n factorial square root e minus I omega t n plus half n. Now this is an eigenstate of the number operator, and this is just a constant, so I can take out the constant, so I can ignore the term that does not have any operator in it, just renders a global phase. So this becomes e minus alpha square over 2 n alpha raised to power n factorial e minus I omega t n. Now what is this? This is really n alpha e minus I omega t raised to power n factorial. Right? And isn't this a coherent state of this kind? So now if I were to so the time evolution of the coherent state goes like this. Okay? If I were to take this coherent state and put it in here, a time factor is going to come here, because now instead of alpha prime, I will have the real part of alpha ei omega t. So this is the state at time 0. At some later time, this factor, I need to replace alpha prime with the real part of alpha e minus I omega t. Right? So this is the real part of whatever alpha you're using. At time 0, the complex number is alpha. At time t, the complex number is alpha e minus I omega t. And what's the real part of it? The real part of that number the real part of alpha e minus I omega t will be alpha prime at some time t, correct? So I need to put this number over there at arbitrary times. So this becomes alpha prime cosine omega t plus alpha double prime sine omega t. Alright? So I need to replace my alpha prime at later time with all of this. At time t equals 0, I just said alpha prime. At later time, the alpha prime, which is the displacement of that operator as a function of position, and sometimes it changes. So at some time, my wave function is here. This is at time t equals 0. This is some position which is given by under root 2. Let's suppose that my alpha is real, to make things simple. So alpha is real, alpha double prime is 0 anyway. So at time t equals 0, my position is under root 2 alpha q naught. This is my position on the q axis for the wave function, for the coherent wave function. At some later time, my position has changed to alpha prime cosine omega t, or alpha cosine omega t. So, but it still remains Gaussian. Nothing else has changed. There is no dispersion. This coherent wave function is traveling in vacuum. This just moves along. At some later time, it comes at under root 2 alpha cosine omega t q naught.
जी से तो आगे पीछे नहीं होता रहेगा फिर
बिल्कुल होता रहेगा,
तो कभी आगे जाएगा कभी पीछे
बिल्कुल
आएगा
होता रहेगा, बिल्कुल होता रहेगा. So if you look at the harmonic oscillator, if you look at the ground state of the harmonic oscillator, the wave function, it reaches the edges and then bounces back. So it reflects back and forth. Okay. So this is how the coherent wave function evolves in time. Okay. So now what we're going to do in our next lecture is we're going to look at multimode fields. And we're also going to look at thermal fields. Thermal fields are mixed states, mixed quantum states. Okay? And we'll derive the Bose-Einstein distribution of photons by an alternative method. Alright? So please do homework number 3 very carefully. I've crafted that homework very carefully so that you can meticulously go through all the questions one by one.